Hi, everyone, and welcome to M2's Maximizing Profitability Opportunities in Design. We're going to give folks a few more minutes to join, so we'll probably be starting in about 2 or 3 minutes. So just sit tight. Thank you. All right, folks, we're going to go ahead and get started. So once again, welcome to M2 Technologies Maximizing Profitability Opportunities in Design webinar. My name is Jasenia. I am the event coordinator here at M2 Technologies. Just a little housekeeping before we get started. I do apologize if there's any kind of background noise. I am working from home and I do live in a busy town, so I do apologize for any background noise. Just a quick reminder, if you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel, not in the chat panel. Also, a recording of the webinar will be available within a couple days, and you're going to receive an email once that recording is available. And just before we jump into the webinar, I want to introduce M2 Technologies to you all. Sorry, folks, give me 1 second. All right, so M2 Technologies is a consulting firm focused on productivity, improving manufacturing process efficiency, and reducing manufacturing costs. Our mission is simple: to help manufacturers design better products and increase market share by leveraging the industry-leading engineering, design, process automation, and data management technologies. Using generative design and best-in-class manufacturing and asset management processes, our team of industry experts can help you become more sustainable, more profitable, and more prepared to meet the demands of urbanization in a rapidly changing world. We're committed to helping clients realize the business benefits of BIM, generative design, and asset management quickly and economically by facilitating the use of innovative technologies and processes. Whether it's streamlining your product design, maximizing asset longevity, or optimizing your processes, our team is one of the most experienced groups of manufacturing technology consulting professionals. We partner with world leaders such as Autodesk, Panzura, and Bluebeam to utilize innovative technologies and methodologies to empower sustainable manufacturing and overcome local challenges. Our vision is to reduce the environmental impact of urbanization by helping the manufacturing industry to design, produce, and operate better projects more efficiently. To help support the industry with these demands of urbanization, we offer a wide range of services, including BIM for manufacturing, data management, generative design at all stages and all levels, CAD management, and much, much more. Now I'm going to let the webinar's host, Tristan Gunderson, hop on. Thank you so much, everyone.
Hi, everyone. I'm Tristan. I'm an applications engineer here at M2. I specialize in supporting our clients in their modeling, design, and simulation needs. So a quick overview of what we're covering today. We're going to give an overview of generative design and how this plays into maximizing profitability. We're going to look at how to assess potential designs, how to run a design study, interpreting the results of these studies, manufacturing these designs, and then the overall benefits that this process brings. So, quick overview, with the current demands of urbanization and onshoring and nearshoring efforts, part optimization, cost reduction, and sustainability are more important now than they've ever been. So using Autodesk Fusion 360 and its tools for simulation and generative design, we can better meet the growing demand and limited resources while lowering manufacturing costs. So generative design, if you aren't familiar with it, is a powerful tool that, when implemented into the design process, assists to quickly explore new and innovative design options. You input models and parameters into the program, and it generates new design outcomes utilizing advanced AI, simulation, and algorithms. Now, I know generative design can be a bit intimidating for some people, so in this presentation, I'm trying to cover a little bit of how it plays into the design process and some of the overall benefits it can bring easily to your designs. So the design process with generative design is you want to start by selecting a design opportunity. Now, this can be a new design that you feel could use generative design to create the optimal design down the road, or by selecting a previous part that you have that could use updating. Now, first you want to do is you want to specify the design criteria and the loading conditions. In order to properly run generative design, you need to have a good understanding of the part, how it interacts with the other parts around it, and the forces that are going to be on it, as well as what the limits of the part need to be and how it needs to be manufactured. So you'll put all that information along with a model into Fusion 360 or a different program if you're using it, and using those parameters that you put in, it will create a series of designs that are made to optimize around those parameters. Next, you'll want to test and analyze the results. There's a few different ways to do it within the program alone or through traditional prototyping. And from there, you can either manufacture the design as you get it from generative design if you have the capability for these kind of manufacturing processes. Otherwise, there's methods that you can either change your design studies to change the design if it's looking good in one regard, but you want to make it better for a different situation. You can go back, change the design studies, and run it again to get new designs. Or you can just improve the design yourself for your current manufacturing process. So one of the biggest hang-ups when people are getting into generative design is trying to find components that would best benefit from this design process. So I put together 5 simple questions you can ask yourself when looking at a design to determine whether it would best benefit from generative design. So the first question is, when was it designed? Older parts tend to benefit the most from this process. Parts that were designed without the use of simulation, FEA, tend to more likely be over-designed, bulky, and use less complex manufacturing processes. So there's usually a lot of extra material that can be cut off of these designs. The next question is, why use this material? A lot of times, materials are simply chosen because that's what was already used, that's what's available in the shop, or sometimes it's because that is a material that was used within the country that it was being manufactured, but for onshoring and nearshoring, that might need a change, or you might be able to just explore different material options that might provide better cost efficiency, be lighter, or be more sustainable. Next is it efficient to manufacture? That's looking at your current manufacturing process. If you're milling something down from a large piece and you're just being left with metal chips afterwards, there might be ways of manufacturing it to take out large chunks instead that are easier to reuse or recycle. So it's a look at that, or looking at other manufacturing processes that might be able to make the same part more efficiently. Then one of the most important ones is, does the geometry serve a purpose? This will eliminate a lot of parts early on. If you're looking at like piping, this probably won't be the most beneficial for generative design because the geometry needs to be watertight. So there's only so much material you can remove while maintaining its design intent. So when you're looking at parts that are made for supporting pieces or connecting pieces, these often will have fasteners at two ends, but the geometry in the middle is arbitrary. So these are some of the best candidates for generative design to redesign that geometry to make it more efficient. And then the last question you can ask is, how is the part currently performing? It seems obvious for if you have parts that are underperforming, they're breaking often, you can use generative design to optimize the strength of the part. You can set a weight so that it either maintains the current material usage, or you can again try and minimize that material usage. But also, if you have parts that aren't seeming to break at all, then it's possible that they are over-designed in the first place, and they too could benefit greatly from generative design. Here I'm going to show you how to set up a design study in Fusion 360. We're just looking at a simple part here. It's just a sheet metal siding to a shelving unit. So the first thing we do is we want to create the components. First, we select the main body here, which is the original geometry. So you see it highlighted in yellow. That's the geometry that is part of the original shape, but is going to be replaced with the generative design for the final product. Next, we are selecting our geometry to keep. This is the basic generative design where we're going to put our forces and the geometry that's going to remain in the final design with the rest of the design connecting it. And then finally, we're going to select our obstacle geometry. We want this any place where other parts are going to interfere, or where we have bolts or other connections. That way the generative design doesn't fill in those gaps. And then we can toggle the visibility on any of these sections or on parts individually. Next, we want to set up the load study. So we're just going to set up a simple load study here saying that each of these shelves is being loaded with 100 pounds down, so 50 pounds per bolt. So we just select all these internal sources, and then you can see on our panel on the side, we can change what units we're using for the force, and we can change the direction type. So we can have it be force normal to the surface. We can have it at an angle, but here we're going to actually use using the coordinate system, because we have our z-axis, which is in the downward direction. We can change the type of force to a pressure, a moment, but we're just going to keep with a simple force for now. So now we have a downward force on each of those bolts. You can see here we have our force and we have our gravity loaded in. Next, what we want to do is we want to make a constraint. This will be at the bolts at the bottom. These would connect to whatever is holding up the side panels here. So we're just going to do a simple fixed constraint, just so those will be held in place so that our forces have somewhere to act on. Right now we have those selected. Hit OK. Next step is setting our design criteria. So we have two general objectives. We can either maximize stiffness, where we can set our target mass and then our factor of safety, but we're just going to go for minimized mass, where we set our factor of safety and then the algorithm runs to minimize the material used around that. And one of our more important steps is setting our manufacturing process. So we have an unrestricted that we could use, which would allow for any kind of shape to be made. We can look at different types of milling. We have 2.5 axis, 3 and 5 axis milling, and we can set the coordinate system in which the tool bits will be coming from. We can set it for die casting, where we can set angle for surfaces, and then we can look at, for this one, we're looking at 2-axis cutting. So we're going to set the cutting tool in the Y direction. And then the last one is the additive processes, would be such as like 3D printing. So for this one, we're just going to leave it with the 2-axis cutting, and we can change the production volume. This will help you with statistics about cost of manufacturing a batch later on. So we can go back. Normally, we'd want to create multiple load cases for the different ways that this part might be loaded in different use. For this one, we only need the one load case, so we're going to continue. We can always create a new study or change the settings for it. And we can see our constraints here and our loads. We're going to take a look at the gravity real quick, and we can see that we have gravity is already acting in the direction we need it to, so we're just going to leave it as it is. And then the last step we're going to do to set this up is we're going to choose some materials. So within this one study, we can try out multiple materials. So you can see here we have aluminums already selected. We'll grab a stainless steel. Now both of these are from the additive material library, so these can be used for 3D printing. So we're going to actually switch to our other library, just the general library, since we're only doing 2-axis cutting. So you can see we have a lot of different types of materials here. We had ceramics. We're going to look at plastics. We'll grab an ABS plastic just to quickly assess the potential for changing from a metal to a plastic for this part. And lastly, we just want to grab one more type of metal. We have an aluminum and a stainless steel. So we're going to go down and grab just a generic steel. You see, it's quite an extensive library. So the other thing we can do is we are able to differentiate what materials are used for the different manufacturing processes we're testing. For here, we're only testing one, so it doesn't matter. And now that we have all these parameters set, we're ready to run our study and get some results from our generative design. So once we've run generative design, it'll output a variety of results for us, and we want to analyze them. So one of the quickest ways to look at the different results from the generative design study is with the charts and statistics that are given to you within Fusion 360. Here you can see a simple factor of safety versus math chart, and the different designs are color coordinated based on the material that was used. So you can see both the stainless steel and the steel had a very high factor of safety, but were also both very heavy. Whereas on the other end, we have our ABS plastic, which came in right at a factor of safety of 2, but the aluminum was even lighter than the ABS plastic and had a higher factor of safety by a little bit there, just around 3. So we'll likely explore that result first. And looking at these results, easiest way is to look at the finite element analysis. Since we've already input the loading cases into the design when we ran the generative design, we can quickly pull up those simulations and see where the weak points are, where we might want to improve the design in the next iteration, or just moving forward to make it into a manufacturable part. And then we also have the potential to run simulations for the tool path with both milling in the 2-axis, 5-axis milling, or to 3D print these parts within Fusion 360. And then finally, once you have selected a generative design study that you feel best fits the criteria for your part, if you have the capabilities within your manufacturing processes, you can use that design as it is. You can export the tool paths directly that you created in Fusion 360. You can use Fusion 360 to design the mold for it if it's a cast part, and you can also create the drawings for the part within the program. Another option, though, however, is if the part itself captures the design criteria, but doesn't quite fit into your manufacturing process how you would like it to, it's easy to take the key features of that generative design and then redesign it for manufacturability. The easiest ways of doing this is by simplifying the geometry, removing and consolidating the small features that it tends to create, flattening features and surfaces. So if you have abstract geometry that tends to bend in different directions, you can kind of straighten all of that out, flatten surfaces so it's easy to mill straight across. And then finally, you can reestablish symmetry. This is good for keeping a consistent manufacturing process, but also can be for aesthetics if that is important to the design. So we're going to actually look at a quick case study for this elevator door drive wheel. So on this drive wheel, there's a chain that pulls along the outside. It's attached at a central axis, and then there are lever arms that connect at 2 points on this door to open 2 doors simultaneously. What we were looking for with this was to reduce the material usage. It needed to still be manufacturable using 3-axis milling. However, other potential manufacturing processes were considered. It needed to have a factor of safety of at least 2. And another important thing was to investigate new material options, as the original part is made of carbon steel, which is a very strong but heavy alloy. So set up the generative design process with the minimizing mass and a factor safety of 2 set for 3-axis milling. And you can see our boundary conditions, created boundaries at the top and bottom to keep the general shape of it, as well as a boundary along the outside to make sure that material didn't fill in between the teeth. And then finally, boundaries for the connecting bolts for the lever arms and the central axis and pin. And you can see in the middle here is the generated result. It cut down material usage significantly and the mass even more. However, it was deemed not ideal for a manufacturing process, so the part was then taken and redesigned using the idea of the 2 hubs around the lever arm connectors with 2 arms, and all of the small connecting pieces were consolidated into 2 larger connections. And through the finite element analysis, it was determined that the weakest point was the connection between the arms and the central hub. So that was also increased a little bit just to easily increase the factor of safety. So when you look at the final results, the material usage went up for the final design from the generative design a little bit, but still overall you can see a reduction by volume of about 30% and a reduction by weight of 75%, with a total factor safety still of 4.3, which is double what was required for the design. So overall, this design process brings a lot of benefits. Right off the bat, it's geared towards creating lighter and stronger parts. These will hopefully last longer, but also put less strain on additional parts and require less material to manufacture. This leads to savings on the material itself, but also using less material and reducing weight leads to reduced shipping costs, and the process can also lead to more cost-efficient manufacturing processes, or by shortening the manufacturing time using the current manufacturing processes. And very important also is the sustainability this can bring. Again, with reducing material and shipping is a huge key to sustainability, but also the ability to use more sustainable materials or to utilize this in the scope of onshoring or nearshoring, which will greatly reduce carbon footprint of shipping materials and parts from across the sea. Also, this system has a built-in rapid prototyping phase. It allows to quickly assess these designs within the program without having to set up additional studies, which allows you to quickly come to a final design without having to create physical prototypes as much. And lastly, it's a much more efficient use of the engineer's time. It allows them to quickly explore avenues. In a typical design process, you might spend a week exploring a new material option, whereas here you can do it overnight. And this doesn't necessarily just mean, it's going to take less time for engineers to come to a design, but more accurately, it allows them to explore more options and create a better design in the same amount of time. And again, all of this helps to benefit the final cost of production and design, as well as creating more sustainable products. All right, now we're going to open up to questions. If anyone has any questions, you can write them in the question box on the GoToWebinar.
Control panel. Yeah, I just realized that I was on mute and I was talking to myself. Sorry, everyone. Yeah, if you have any questions, please feel free to ask them in the questions box in your GoToWebinar control panel. We'll give it just another minute. Also, if you think of any other questions that you may have after the webinar, we are always open to answering questions. You can reach out to us on our website, give us a call, email us, reach out to us on our social media platforms. We're absolutely here to help with generative design at any stage of the process. We understand that it can be a little intimidating, so we're here to help. But if there are no more questions, or if there are no questions, which I don't believe there are, then we can just end the webinar here. Thank you all so much for attending our webinar today. We look forward to seeing you at our next webinar soon. Thank you so much, Tristan, as well. And have a great day, everyone. Take care.